Welcome back. In the previous section, we talked about linear regression, where we had output values that were a continuous variable, so they could take on any real number. In this section, we are gonna take a look at a different topic, logistic regression, where we'll see how we can deal with output values that take on discrete numbers or categorical variable. In the previous section, where we talked about linear regression, we had two features, petal length and petal width, that are both continuous variables and can take on any real number. And we wanted to know whether there is a relationship between these two features. So, looking at the data, we decided to go with a linear model that took the form of wx plus b. And now we are asking a different question, which is whether we can use petal length to distinguish between different plant types. So as input, we have the petal length, which is a continuous variable, but as output, we only have two possible outcomes, either versicolor or virginica. These kind of tasks where we have categories or classes as the output are commonly referred to as classification. And since here we only have two possible classes, then we have a binary classification problem, also known as logistic regression. And now the question is, what is the function that is suited for this binary classification task? In the next few slides, we are going to discuss the function that is suited for this problem. And similar to the previous section, we'll define an objective function so that we can use gradient descent to find the best model parameters. Let's get into it. As a first step, to be able to work with numbers and fit our model, let us assign some numerical values to our classes. Here I'm assigning 0 to versicolor and 1 to virginica. Let's start with what we already know, and that is a linear model with mean squared error as the loss function, and see if we can use it for this problem. And indeed, we can use a linear model if we combine it with some thresholding mechanism. So imagine we use a linear model and fit the model to the data with mean squared error loss. And once we train the model, we can then use a threshold of 0.5, for example, in this case. And if the model outputs any value above this threshold, we just assign the value 1 to it. And if it outputs any value below the threshold of 0.5, we just assign that to 0. But using a linear model with MSE loss, in this case, does not work very well. And that is because it is sensitive to outliers. So imagine we have some data points around the red point in the figure, and the problem is that the error that we get for this data point is much bigger than another data point that is more centralized. And so this means that our loss value would be dominated by these outliers, these data points that are further away. And this would result in a model that is biased towards these outliers, just because they result in a much higher loss value. So we need to come up with a better model and also a more suitable loss function. Another option is to just use a threshold on the feature itself. And if the value is above the threshold, we set the output to 1, and if it is below the threshold, we set the output to 0. So this is how the function looks like. We have a threshold, and anything above the threshold is set to 1, and anything below the threshold is set to 0. And this function actually has a name, and it's called the Heaviside step function. Okay, let's now formalize this function and use it for our binary classification problem. Here we have the function equation written down. If x is above 0, which is our threshold, then the output is 1, and otherwise the output is 0. And now I'm going to put the data on the same axis, and if we go ahead and apply the model on the data, everything will be classified as virginica because all the values are above the threshold, which is not ideal. What we can do is to shift the data such that the threshold at 0 becomes more relevant for the task, and we get a more reasonable output from the model. And that means that we need to add a bias term to our function such that the data can be shifted. At this point, this is looking very similar to a linear model that we had in the previous section, except that W is 1 in this case. So we might as well go ahead and define a generic form of the function and just keep in mind that W is equal to 1. All right, so far we have specified our model, and the only parameter we need to learn is the bias parameter B. And now we are ready to define the loss function and then use gradient descent to find the best value for our model parameter. So let's try to come up with a reasonable loss function. We know that our target values are either 0 or 1, and our model can also output either 0 or 1. So in total, we have 4 combinations, where in 2 of the combinations, the model output and the target are the same, and in the other 2, they're not the same. And so one option for the loss function could be to just count the number of times where the model and the target disagree. So every time that our model output and the target are not the same, the loss value would be 1, and if our model makes the correct prediction, then the loss is 0. And now let's go ahead and look at the loss landscape as a function of the model parameter B. So this is how the loss landscape looks like, and the final step is to make an initial guess for the parameter value and then use gradient descent to move down the valley. But there is a problem. Can you identify the problem? Just to give you a hint, remember the analogy of moving down the hill in a foggy weather. And maybe pause the video and think about the problem here for a couple of seconds. The problem with the loss landscape is its stepwise nature. And on these steps, the gradient is actually 0. And so since the gradient descent relies on gradient information to update the parameter, it would fail here and our parameter will not get updated. So we have a problem, and to find a solution, we need to figure out why does it happen? Why the derivative of loss with respect to our parameter is 0. To demonstrate the problem, first I'm gonna rewrite the derivative of loss with respect to the bias as a multiplication of 2 derivatives. The first one is the derivative of loss with respect to our model output. And we can do this because the loss function is actually a function of our model output. And similarly, we can also write the derivative of our model with respect to the parameter B, because our model is also a function of the parameter B. And writing it this way is equivalent to the original derivative of loss with respect to the bias, simply because you can cancel out the df in the equation and you get the original derivative back. What we just did here is called the chain rule, and Arne will talk more about this in the later sections. Okay, now rewriting the derivative this way would allow us to investigate each of these derivatives individually. And then we can see if any of them is causing the problem. And in this case, the problem is with the derivative of the model output. We can see that both visually and from the equation, that since the output of the model is a constant, then its derivative with respect to any of the parameters would be 0. And since this derivative is 0, it causes the whole term to be 0, so the derivative of loss with respect to the bias ends up being 0. Now that we identified the problem, what is the solution? So we know that the problem is actually with the model. Because it's a step function and has constant outputs, its derivative would be 0. So the solution is to replace it with a function that does not have constant output, but at the same time, we want it to look similar to the step function. In other words, we want to have a smooth approximation of the step function. And luckily, such a function exists, and it's called the sigmoid function. And now, using this smooth approximation, we can avoid the problem of having 0 derivatives. But the important take-home message here is that to use gradient descent, we need to construct the model from smooth functions. All right, now let's come up with an appropriate objective function to finally train our model. So what do we want the model to do? What we want is that when the target value is 1, we want the function output to be as high as possible. In other words, we want to maximize the function value. And since the output of the sigmoid function is bounded between 0 and 1, this means that we want the output to be as close to 1 as possible. And when the target is 0, we want the function value to be as low as possible. Minimizing f of x is equivalent to maximizing 1 minus f of x. So let's use this so that we have a maximization in both cases. And this way we can just give our objective function a name. I'm calling it h in this case. And the goal is to maximize this objective function. And now I'm going to simplify this objective function a bit and write this as a single line equation. And this is exactly equivalent to what we have above. So for example, if yn is equal to 1, this term is f of xn. And here the exponent would be 0, which means that the term here on the right would be equal to 1. So we are left with f of xn, which is exactly what we want. And you can go ahead and try for yn equal to 0. And what you will see is that we'll be left with 1 minus f of xn, which is exactly what we want. So the two are exactly the same. Now, a common practice in machine learning is to take the log of your objective function, and this is because people have shown that this results in a more stable training of the model. So let's go ahead and take the log of our objective function, and now we have a complete objective function for a single data point. To take all the data point into consideration, we simply apply the function on all data point and take the average. One last point is that since the objective function is also commonly called the loss function, then conventionally it is minimized rather than being maximized, because you usually want to minimize the loss. And so far we have a function that we want to maximize. But we can simply make it a minimization problem by just taking the negative of our original objective function. And with that, we have our complete loss function. And now it's time to look at the loss as a function of our model parameter. Now, remember that we went through all this trouble because our original loss function was not smooth. It was like a step function with 0 gradient, and so we could not use gradient descent on it. So now let's look at the loss landscape and see if the trouble was worth it. And indeed, we see that we get a smooth loss landscape, and we can use gradient descent to find the optimal value for the model parameters. One last point is that the loss function that we derived here together is actually a commonly used loss function for classification, and it's called the cross entropy loss. Just in case if you're interested to look it up online. Let's summarize what we talked about in this section, which was about logistic regression, also known as binary classification. We specified the model, which ended up being a linear model combined with a smooth approximation of the step function, called the sigmoid function. And the important take-home message was that in order to use gradient descent, we need to construct our model from smooth functions. Then we derived the objective function, the cross entropy loss, and altogether we got a smooth loss landscape which allows us to use gradient descent and find the optimal value for the bias parameter. We're almost done, but before we finish this section, I want to talk a little bit more about one possible way to improve the model. So far we've been using a single input feature, the petal length, to distinguish between the two types of iris flowers. But using this single feature results in some false predictions. So as you can see in the figure, for some of the petal length values, our model would assign them to the wrong class. How can we improve this result? In other words, how can we reduce the false predictions? One option is to use more features. So here we can add an additional feature, petal width, and then use both features to perform the classification task. So now we'll have a two-dimensional feature space, and the color shows the different classes. All right, now that we have two features instead of one, let's see how that changes the model. And the model does not really change that much, except that now we have this additional weight parameter for our additional feature. So we still have a linear model that combines the two features plus the bias term. And I'm calling the resulting variable z just to write things a bit cleaner. And then we pass that to our sigmoid function to get the final model output. Here is the graphical representation of this model, and I'm showing this here just to familiarize ourselves with this representation, because later on we'll see more of these graphical representations. So we have the input features x1 and x2 and their corresponding weight parameters w1 and w2. And plus a bias term, which is usually not shown in the graphical representation, that gives us z, and we pass that through the sigmoid function to get the model output. So remember that in the previous case where we had a single feature, we were looking for a threshold to perform the classification task. And now that we have a two-dimensional feature space, we are looking for a line in this 2D space that separates the two classes as best as possible. This line is commonly referred to as the decision boundary. So everything on the one side of the line would be assigned to one class, and everything on the other side would be assigned to the other class. And finally, since we are only changing the number of inputs and nothing changes in the output, we can use the same cross-entropy loss that we've seen before as the objective function and use gradient descent to find all the parameters of this model. So we just learned how to define a model for a two-dimensional feature space and find the decision boundary to separate two classes. Now, I want to end this section with a question for you. How can we use what we've learned so far to separate the two classes here? If you're curious about the answer, continue to the next section where Arne would tell us all about it.